Welcome. On this lesson, we're going to take a look at the limit of functions, and we're going to be doing that by performing some extra examples. So let's take a look into this now. So for example 1, it states, for the following equations, let's find the given limit either by graphing or performing some table of values, and then let's evaluate the function at the limit point. So what exactly is going on in example A? Well, in example A, we have the function 8 minus 3x plus 12x of x squared. And we want to see what's going on to this function as x is getting closer and closer to 2. So how are we going to perform that? Well, recall that if we want to take a look at the behavior of this function, if we want to take a look at the limit of this function, and if the limit point is a value of 2, what we're going to do now is we're going to be performing table of values. So if this is 2, we're going to be choosing some points that are on the left-hand side of 2. And then we're going to take a look at some points that are on the right-hand side of 2. And we're going to see if they actually are approaching the same value. So how do we do that? Well, let's go to our table of values. So let's go to Desmos now. So here we have the function 8 minus 3x plus 12 of x, which seems to be a parabola, which is fine. But let's actually take a look at the table of values for this function. So let's take a look at the table of values. And I notice that we have some random points here. X equals -2, -1, 0, 1, and 2. But these are not the points that we're looking for. Because again, if we want to take a look at the limit as x approaches 2, I'm going to take a look at some points that are on the left-hand side of a value of 2. Well, I don't know. Let's choose some points. Let's say this is 1.99, and then 1.98, and then 1.97. So notice that I'm just choosing some points that are on the left-hand side of 2, but now notice that they are just getting super closer and closer to the value of 2. So let's put that in here. So for x, let's do 1.97, then follow a 1.98, then 1.99. But now notice that as we're getting closer and closer to 2 from the left-hand side, we seem to be approaching the value of 50. I don't know, let's take a look at one more. 99, oops, sorry, that's an extra one there. 1.999. Notice that we're just getting super closer and closer to the value of 2 from the left-hand side. So from the left-hand side, if we take a look at the behavior, we seem to be approaching the value of 50. So let's write that down. So I'm going to introduce you to a new notation. So to say that we want to take a look at the limit of the function as 2 it's approaching from the left-hand side, we're going to indicate that by putting a little negative on top of the 2. So what this is saying is, if I take a look at this function, as x is approaching 2 from the left-hand side, we seem to be approaching the value of 50, because that's what we just observed here. Notice that if I'm getting closer and closer to 2, my y values are just getting closer and closer to the value of 50. So now, let's take a look at the behavior from the right-hand side. So if this is 2, and if I want to take a look at the behavior from the right-hand side, let me just choose some points that are on the right-hand side of 2. What are some good points that we can choose for? Well, perhaps we can choose the values 2.01, 2.02, 2.033. So notice that all I'm doing is I'm just choosing some values that are just getting closer and closer to 2. And let's look at the behavior of them. So now we go back to here. We got 2.01. And the next value that we're interested in is 2.02. And the next value is 2.033. So let's take a look at the behavior now. So from the right-hand side, we go from 51. Then as I'm getting closer to 2, I go to 50.9. And I get a little bit closer to 2, and I get to 50.45. So it is fair to say that also from the right-hand side, I'm also approaching the value of 50. So how do we write that? Well, again, to indicate that we want to find the limit of this function from the right-hand side, x approaches 2, and to indicate that this is from the right-hand side, we're going to put a little plus on top of it. So now what this is saying is, I'm looking at the limit of this function as x is approaching 2 from the right hand side, and from the right hand side we seem to be just getting closer and closer to 50. So now notice that if I approach it from the left, I seem to be getting closer to 50. And if I approach it from the right, I seem to be getting closer to 50 as well. So therefore, if the left is equal to the right, now we can make the full claim that the limit of this function as x is approaching 2 is equal to 50. And again, all we did here, we just took a look at the behavior of the function. We take a look at the behavior of this function as 2 from the left. We take a look at the behavior of this function at 2 from the right. We saw that they're meeting the same point, which is 50. So therefore, the limit should be 50. So how do we visualize that in a graph? Well, here we have our points. Notice that these are the points that we're tested on. Let me actually write this because this is a little bit convoluted. So here we have a function without all those points. So as we were getting closer and closer to 2, so let's see, where is 2? 2 to be about here, 50. Turns out if we approach at 50 from the left-hand side, if we take a look at the y values, we seem to be approaching the value of 50. And again, if we would approach it from the right-hand side, notice that we're also getting approaching to the value of 50. So if we come from the left, you approach 50 as x gets closer to 2, and you approach it from the right, you also get approaching 50 as you're getting closer to 2. So therefore, if the left equals the right, then that's the limit. And that's exactly what we just wrote here. So now let's evaluate this function at the value of 2. So now let's take a look at some evaluation. So what would happen to this function if we evaluate it at 2? Well, let's see. So now we're going to get 8 minus 3 times 2 plus 12, 2 to the second. So now this becomes 8 minus 6 plus 12 times 4. So 8 minus 6 plus 48. So now 8 minus 6, that's 2. And 2 plus 48, that's equals to 50. So notice that we got the same value if we were to just evaluate the function at 2. So that's just one way to realize what's going to happen here. But now, let's be careful with this evaluation method, and you will see it on the next example. So let's take a look at the next example. And again, we're just going to take a look at example A and B. We're not going to talk about C today. So here we have B. And again, here we have our function 2z squared minus 7z plus 8 all over a minus z. And we want to find out what happens to this function as z is getting closer to 8. And again, the way that we do this is we're going to think about it as if it was some kind of a number line. Let's say that this is the point that we're interested on, 8. And we're going to be taking a look at some values from the left-hand side as I'm getting closer to 8. And I'm going to take a look at some values from the right-hand side, and I'm going to make them get closer to 8. And we want to see what happens when they both approach 8. Do they both approach the same value? Well, let's find out. So here we have a function. So let's erase this. So this is a function that we're interested on now. So this is a line. This is a linear function. That's fine. So what are we interested on? We're interested on this function as z is getting closer to 8. So let's take a look at some table of values here. So here we have our table of values. Let's choose some points that are coming from the left-hand side, getting closer to 8. So from the left. So here we have our table of values. Let's just choose some values that are on the left-hand side that are getting closer to 8. So I don't know, 7.97, 7.98. Notice that all I'm doing, I'm choosing some points that are getting closer to 8, coming from the left-hand side, 7.99. And if we take a look at this behavior, and let's just do one more, 7.999. If we take a look at the behavior, notice that as I'm getting closer and closer to the value of x equals 8, my y values seem to be getting closer and closer to the value of negative 15. So let's write that down. So from the left hand side, the limit as z is getting closer to 8 from the left hand side of the function 2z squared minus 7z plus 8 all over 8 minus z, we seem to be getting closer and closer to negative 15. So now let's take a look at the behavior from the right hand side. Let's choose some values that are on the right hand side of 8, which are just getting closer and closer to 8. So I want to start with 8.01, 8.02, 8.03. Let's see. So notice that I'm just choosing some values that are on the right hand side, and these values, as I get it closer and closer to the value of 8, the y value seems to be getting closer and closer to negative 15 as well. So therefore, let me write this down. So the limit as z is approaching 8 from the right hand side of 2z squared minus 17z plus 8 all over 8 minus z, that's equivalent to negative 15 as well. And since the left hand side it's approaching to negative 15 and the right hand side it's approaching negative 15 as well, then therefore the limit of the function as z gets closer to 8 of 2z squared minus 17z plus 8 all over 8 minus z, then therefore that's equivalent to negative 15 as well. Oops. Negative 15 as well. So let's just try to visualize what just happened here. So let's take a look at my function here. Let me eliminate my table of values. So here we just have the graph. So let's see, where is exactly the value of 8? Well, 8's about 5, 6, 7, 8. So that's about here in my function. So if I'm approaching from the left-hand side, notice that as I'm getting closer and closer to x equals 8, because again, notice that here's 8, so 5, 6, 7, 8. So I'm looking at this point in our graph. So if I'm approaching it from the left-hand side, I'm getting closer and closer to negative 15. And if I'm approaching it from the right-hand side, I'm also getting closer and closer to negative 15 as well. But notice what's happening at the value of 8. It's an undefined value. So what exactly does that tell us? Well, if we go back to the function, the way that it's been written out, if we substitute 8 to the function right away, notice that we're going to get a 0 on the denominator. If we substitute z equals 8 to the denominator, we're going to get 0. So therefore, we're going to have an undefined value. So notice that when z is equal to 8, we have an undefined value, but we know that the limit is negative 15. So how is that possible? If I substitute 8, it's an undefined, but the limit is negative 15. Well, one way to realize what's going to happen here is to factor out the numerator. So let's factor out the numerator and let's see what happens to that simplified version of the original function. So if we factor out the numerator, we're going to end up with 1 minus 2z and 8 minus z. And the denominator is still 8 minus z. So by doing that, notice that now they're going to cancel out. And now we're going to have 1 minus 2 of z. So if we take a look at the simplified version of the original expression, and we substitute z equals 8, we're going to end up with 1 minus 2 of 8. So that's 1 minus 16, which is negative 15 as well. So this is a very important problem because this is going to address many questions that some students are going to have. Because one misconception that I have seen from students is that anytime that you're looking for the limit, you are just tempted to just substitute the value to the function and then treat the result as being the limit. Well, this is one of those examples where that technique doesn't apply, because if we just substitute z equals a right away to the function, We just saw that it's an undefined number. So you might be tempted to say that the limit is undefined. But we just saw that the limit is negative 15. And the way that we get that value is by simplifying the numerator. And notice that we got the same value as the limit. So it is not good to just always substitute the value to the function and make that your limit, because again, the limit doesn't refer to us to what's happening at the value z equals 8. The limit is the idea of what's happening to your y values as you're getting closer to 8. So we don't care too much about what's happening exactly at 8. We wanted to see what's happening as we're getting closer to 8. So be careful with these type of examples now. So the last example that I do want to address is the following. One where a graph is being given to you. So for the example 2, so here we have a piecewise function. It's just a piecewise function with some holes, some gaps, and everything between them. And what we want to do is, let's just find some limits. So if this is my function, let's try to find some limits. So let's take a look at 1 through 4, because that refers to the same points. So let's answer that. Let's discuss this now. So here we have our graph, and at least for example 1, it states, let's find the limit of f of x as x is approaching negative 3. You know that we have a little negative on top of it, so that means from the left-hand side. So let's look at our function. Let's see what happens to the behavior of the function as we're getting closer to negative 3 from the left. So here is negative 3. And notice that if I'm approaching negative 3 from the left, I seem to be getting closer and closer to the y value of 1. So negative 3, it's right here. If I approach negative 3 from the left-hand side, so I'm just writing this wave right here. And as I'm getting closer to negative 3, I'm also getting closer to the y value of positive 1. So let's just write that down. So negative 3 from the left is positive 1. So how about negative 3 from the right? So here's negative 3. Now if I approach it from the right, I'm just making this movement. And then from here, I'm just going to go down. And notice that I'm also approaching the y value of positive 1. So now notice that the limit from the left, it is equal to the limit from the right. So therefore, the overall limit is 1 as well. But notice what's happening now. What's happening as f exactly at negative 3? Well, this is f, and at negative 3, we have a hole. So at negative 3, the function itself, it's undefined. So this is kind of like what we were looking at example 2 previously, where we do have a limit, but if we just substitute it, we have an undefined value. So we got to be careful with that. Let's take a look at examples 9 through 12 now. From 9 to 12, we're looking at the value of x equals 2. So where is x equals 2? So here we have x equals 2. So let me actually just, let me not do that. Let me just do it in red, just to indicate that this is the value that we're interested on, x equals 2. So we want to approach 2 from the left, because notice that we have a little negative on top of it. So if this is 2, and if I'm getting closer to 2 from the left, I'm just writing this function right here. And then notice that if I'm approaching 2 from the left, I seem to be approaching the value of positive 2. So 2 from the left is positive 2. And now 2 from the right, so here we have 2. And if I get closer to 2 from the right, notice I'm just going to be following this function. And if I'm getting closer to 2, notice that I'm getting closer to the y value of 1. So notice that from the left, I approach 2. And from the right, I approach 1. They don't approach the same value. So therefore, the overall limit, it does not exist. Because the limits will only exist if the left and the right approach the same value. And this is very important. This is why we have this little notation here. The limit will only exist if the left and the right approach the same value, which in this case, they didn't. If I was approaching 2 from the left, so here's 2, from the left, I was approaching the y value of 2. and from the right, I was approaching the y value of 1, they don't approach the same y value, then the limit does not exist. Well, what's happening exactly at the function at the value of positive 2? Well, at 2, notice that we have a hole on 2, and we have a solid at 1, so therefore the value f, the function f evaluated at 2 has a value of positive 1. So with this, it concludes our lesson of limit of functions and taking a look at some practice examples.